What's up guys? Welcome back. Today we are going to doing a full walkthrough of Tryhackme room AI models and data. And this room is all about how data shapes AI security. And trust me, if you are in AppSec or doing bug bounty or planning to move into the AI security, this one is a foundational course for you. I am Ashwin Govin. Let's get into it. Welcome to Hackerla. So task one, which is introduction. So let's start with the what room tells us, and the room opens with this. So every AI models is at its core a product of training data. Before a single prediction is made or a single prompt is answered, decisions about what we or what data is collected, where to or where it collected from, and how it is processed, it have already shaped everything the model ever do. So that's a core idea. Everything we cover in this room flow from this thing. So this room then lays out 5 learning objectives. So understand where AI training data comes from, the security risk introduced by poor data provenance. Recognize how the PII and the sensitive credentials can be become permanently embedded in the model which through large scale web scraping. Understand how key model building decisions, overfitting, quantization, and federated learning each introduce distinct security risk. Understand the inheritance problem and what organization unknowingly take on when the fine tuning pre-trained models. Recognize where trained data or trained models are opaque black boxes and what models can do and fail to do to address this. And the prerequisite of this room, its list is basics of AI/ML that we already covered in the first session. It should be understand, and you have to cover this AI/ML security threat room before jumping into this room. So if you haven't done this room, you just go to the first video, and for task one, only question is just answer it. I understand the learning objective, and I'm ready for the learn about the AI models and that. So just click it, complete, check and complete the task one. Let's move on. Task number two, training data. So task two, where the real content starts. Let's start. Where does the data come from? So the room asks a question that most people ever or never think about it. So collected from where and cleaned by whom? So that's the key question. The room explained that the pipeline typically draws from 4 buckets. And let's see, there's a bucket or there's a table here. The source, what is it? Trust profile. So there are four different sources, and it's explaining what it is and the trust profile. So let's understand this thing. First one is the source, which is scrapping. So what does this mean by automated crawls of the public internet? Contents or content, news forums, blogs, social media, etc. These are the web scraping sources. How can we trust that? So low or no curator, no version control, content change after collection. Okay. So next one is licensed datasets. So data purchased or agreed with the platform, example OpenAI, Reddit, Metas on social media posts. These are the licensed datasets. What is the trust profile or trust? How much we can trust? So it's medium. Terms often unclear. Original users rarely concentrated on AI training use. Next one is synthetic data. AI generated content used to train the further AI systems. So how much we can trust? It's variable. Growing fast is 12% of fine tuning datasets now contain LLM generated content. And the final one is internal Cobra. Company knowledge bases support transcript clinical notes used for fine tuning. So how much we can trust? Higher. Organization have direct control but also direct liability if it is mishandled. So now the room tells what the mostly widely or most widely used data sets is. So the most let's go through this. The most widely used data set is Common Crawl, a free publicly available web archive or web available archive of web crawl data that has underpinned essentially every major model family. So DeepSeek V2 was pretend on it. DeepSeek V3 uh, which is trained on 14.8 trillion tokens with the common crawl as a core source. And Llama 4 was scaled 40 trillion token across the 200 languages using a similar pipeline. So that's a massive scale. And let's check into the highlighted thing, which is GPT-3 is a one of the few models whose breakdown is a publicly documented. 60% of its token came from filtered version of Common Crawl. Okay, and more recent models lean even more heavily on it. The keyword filtered and how the filtering was done by whom and what slipped through is where the security story began. Right. The filtering is everything. So what slipped through this whole problem? And the problem of provenance. Let's go through that. The room data, or let's look into it. The room defines the data provenance as the ability to answer three questions any piece of training data. So first one is where did it come from, and second one is when was it collected. Third one is has it been modified since. So and the honest answer for the most models, let's look into it. In most AI supply chain today, the honest answer to all three, we don't know or we don't fully know. So the room reference an audit. So the data provenance initiative audited over 1,800 data sets and found that more than 70% of licenses on popular hosting platforms were listed as unspecified. And of those that were labeled, 66% were miscategorized, usually listed as more permissive than the actually were. So think about that from a legal and security perspective. The organizations fine tuning on these datasets often have no idea. So what they legally have, let alone what inside it. So the room draws a great comparison here to the software world. So the software or the solar wind taught us the industry that you can't trust a compiled binary if you don't know what went to it, which is exactly software bills of material, which is the SBOMs, become standard practice. The AI equivalent of the ML-BOM, a documented inventory of dataset sources, licenses, PII category, and filtering decisions. So ML-BOM, just remember that term. That is going to be a something in the Q&A answer. And PII in the pipeline. Now the room gets more scariest part because we are going to talk about the PII. So one of the most direct consequences of undocumented large-scale web scraping is that personally identifiable information ends up the backed into model weights. One is there, it's very difficult to remove medical records, personal email threads, forums, posts about the health condition or political views, all of which get swept up this. It was publicly accessible at the crawl time. So here is the real world concrete examples that this particular room gives us is truffle security scanned the December 2024 common crawl archive 400 TB of data from 2.6 billion web pages. Okay, and found nearly 12,000 live verified API keys and passwords. So, with the right prompt, a model trained in that data can sometimes coax into surfacing training content near a verbatim, including credentials. So 12,000 live API keys. Just so these things baked into the training data, and this room makes this point in a crystal clear way. So this isn't a bug introduced by an attacker. It's a consequence of what went during training, and no patches fix it on one model if it is deployed. So no patch. So once it waits, it fits in. That's the thing. So that's the key takeaway from this point. So now let's answer the task number two questions, and uh, these answers are straight from the thing just we covered. So question number one: What terms uh, what terms describe the ability to answer where data comes from, when it was collected, and whether it has been modified? So what is the answer? It's the data provenance. Question number two: What is the name of mostly or most widely used public corpus that underpins essentially every major model family? So that's we already covered from the initial itself. Everywhere it's mentioned the common crawl. Common crawl is the basic. Let's add that one, common crawl and data provenances. Okay. Okay, answer correct. So question number three: What is the AI equivalent of software bills of material? So as I mentioned, it's already like which is used to document the dataset source, licenses, and filtering decisions. It will be ML-BOM. Okay, it's correct. Let's move to the task number three: building the model. So this task number three. Let's go inside the model, how the building process, everything works. So building the model, key concepts. So this room is covering some four key concepts here. So each with different security implications. Okay, let's look into it. Epochs and overfitting. So let's see what it is. This epoch is one complete pass of training algorithm through the entire data set. In practice, models are trained over many epochs. The algorithm repeatedly seeing the same data, adjusting its parameter each time until it cover on accurate predictions. Oh, okay. It's simple. It's simple enough, right? So, but here is the problem. Problem starting. The catch is that more epochs don't always mean to a better model. So, train for a too long, and the model steps learning general patterns and start memorizing training data specifically. A problem called overfitting. So, and the security angle on this is let's read this one. This matter for a security because overfitting is one mechanism that or by which a model can memorize specific details from the training data, including sensitive one, making it more likely to reproduce when it is prompted. So as we understand, overfitting isn't just a performance problem. It's a data leakage risk, right? That is what I understood. So if you have anything, just mention or just comment here. So next one, model validation. Let's see how this room explains the model validation. So to catch overfitting early, a portion of this training data is held back and never used for training. So this is the validation thing. And at the regular intervals during training, the model is tested on unseen data to check whether the performance is actually generalizing or just improving on the training examples it seen before. So let's go through the same security implications. From a security perspective, validation is the quality gate in the ML life cycle. A model that skip through the validation is one a real world behavior is unknown, and such unknown behavior is a security risk. That means a bias and anomalies introduced through compromised training data may undergo undetected until the model is already deployed. So unknown behavior equals the security risk. So that's the line to remember from this point. Post-training optimization, pruning and quantization. Post-training models get compromised. The room gives us a table here. Technique, what does it or what it does? Security consideration. So the two technique, pruning and quantization, what does it? So pruning is remove the parameter that contribute the little to predictions, shrinking model size. So the security consideration is change model behavior post training, rarely documented in detail. Quantization means or what it does is reduces numerical precisions of weight, example 32 by 2 8 bits floats, to cut memory and compute requirements. So the security consideration is can degrade safely aligned behavior. Backdoor defenses tested on full precision model may fail to detect threats in quantized versions. Okay, this here it is explaining why this is matter. Both steps are applied after the training is completed, often by a different third party. The team packaging the model or distribution model for distribution. Research has shown the quantization can silently degrade the safety mechanism built into model. Defenses that worked on the fully precision version may fail to detect backdoors on the model is compromised. When an organization download the quantized model without documentation or of what changed during compression, they are inheriting unknown behavior modification alongside efficiency gains. So that's the that last phrase. It's mentioning like so inheriting unknown behavior modifications. So that is what you need a you need something. So in this particular room, mm, or you need to flag in this AI risk assessment. Federated learning. So let's look into it. What is federated learning? The model is trained across many decentralized decision or organizations, which with each participant training locally on their own data and only sending weight updates, not the raw data itself, back to a central server for aggression. So the privacy benefit is real. That's what. So a hospital sharing patient record to train a model is a data protection problem. A hospital contribution model update without ever sending the records is much easier conversation. So, but the security trade-off. Let's look into this one. The integrity of the training process become much harder to verify in a centralized setup. The organization that trains the model control the data. In federated setup, participant can submit poison local updates, subtly manipulated this gradients designed to skew the global model's behavior. And these can be very difficult to detect at the aggression stage. And here it is summarized perfectly. The question shift from who controls the data, who controls the aggression, or who controls the data to who controls the aggression, and can any participant corrupt it? So that's your attack surface federal learning. So let's answer these questions. Question number one, task, which is what term describes one complete pass of the training algorithm through the entire data set? The one which we learned is epoch. EEOCH. Yes, correct answer. What problem occurs when the model memorizes training data rather than learning general patterns? Mm, the second point, which is overfitting. Let's enter overfitting. That works. What post-training optimization technique reduce the numerical precision of model weights, cut memory and compute requirements? That is a point that is in the table itself. Post-optimize technical reduce the number of precision. It's quantization. QUANTISA1. Yes, that's correct. What training approach trains a model across decentralized devices, sending only weight updates rather than raw data to a central server? The last point, which is uh, let's scroll federated learning. Let's copy and paste. That's correct. Let's look into the task number 4, which is the inheritance problem. So task number 4 is arguably the most important task in this room from practical security standpoint. That is what pre-trained models and fine tuning. So the room here, let's see the context. Training an LLM uh, from scratch means assembling trillions of tokens of data, acquiring the compute infrastructure to process it, and running a training job that can cost tens of millions of dollars. For most organizations, that's not a realistic option. So here, everyone use the pre-trained models. So that is a common thing. Everyone is using. So let's see how it defines. A pre-trained model is one that has already been trained on a large general purpose data set. These base model learn broad languages, understanding grammar, facts, reasoning patterns, and world knowledge. They are proven by a small number of well-reduced organizations and then made available for those to build on either through open weights like Meta Llama family or through API access like OpenAI's GPT series. So what is fine tuning? Fine tuning is the process of continuing to train one of the pre-trained models on a smaller task specified dataset. Now, let's see here the critical decisions in the room explains. What fine tuning changes? The model's task specific behavior, tune and domain knowledge. So, what fine tuning does not change? The base model weights, the billions of data parameters based by the pre training on the data. The fine tuning organization never saw, almost certainly never audited. So you can read that again. The base weight for that shaped by the data, you never saw that. That is a major point, and those datas are never audited. So it's there is no change as well. So that is what basically this fine tuning. And next point, which is the inheritance problem. So that's the inheritance problem. The room basically spells out it. So when you fine tune a predefined or pre-trained model, you inherit everything that model already contains. So this includes things you cannot see and do not choose. And here three points to show up are safely align the roads, not brakes. Let's go through that. Stanford and the Princeton found that the defense mechanism of aligned LLMs can be compromised by fine tuning on a few as 10 advisory craft example at the cost of under $0.20. Even denying the fine tuning on legitimate data degraded safely as an effect. So here is a brilliant analogy. Think of a safety alignment like a well-worn path through a forest. So the model has been trained to follow this safe path when generating responses. Fine tuning is like adding new path through the same forest. Even if there is those new paths are legitimate, like teaching medical terminology, they they can gradually obscure the original safe path. So the model hasn't forgotten how to be unsafe. The probability weights have just shifted, making unsafe responses likely again. So the defense mechanism don't snap, they wear down. So specialization increase the attack surface. Next one is Cisco found that the fine-tuned models are measurably more susceptible to a prompt injection than the base model they were fine-tuned for. So the reason is structural. Fine tuning narrows the focus, reducing the resilience of to unexpected tokens. Think of it like this: a model fine tuned on a financial record gets better financial reasoning, but also becomes more responsive of attacker who frames their prompt into financial terms. Okay, that's a point we have to look into it. Version matters and it's rarely tracked. Fine tuning always targets a specific checkpoints of a base model. If that checkpoint later turned out to contain a backdoor or problematic training data, every derivative inherits it, regardless of whether anyone downstream was told. So, and this task was lined up uh, this kind of details. So, when your organization deploys a fine-tuned model, you are not deploying the fine-tuning work your team did. So you are deploying the entire pre-trained base beneath it. That's a base was shaped by a training process. You didn't control it. On the data, you didn't audit by an organization whose supply chain almost certainly have been reviewed. Task number 4. And the questions which we are going to answer is: what is the process of taking pre-trained model and continuing to train into a smaller specific task or smaller specific data set, which is fine tuned? Fine-tuning. That's the correct answer. That's correct. What's the term describes a model that it has already been trained on a large general purpose data set? That is pre-trained model. Trained model. That's correct. Let's look into the task number 5, the black box problem. So task 5 is the, I think, last theory task. So models are actually black box. Models are a black box. So just what is it? It covers, I think it covers why you can't just inspect a model the way you didn't inspect the code. Okay. So when a security problem or security team want to audit a piece of software, they have options. Source code is a readable. Even compiled binaries can be disassembled, step through and reasoned about it. So a trained model weights are neither they are billions of floating point numbers, the cumulative result of the training process, and they carry no human readable records on of how they were shaped, what data influence them, or what behavior they encode. So this is the now let's look at the key implications. This means trusting the model is fundamentally trusting the process that produced it. So you can test its behavior, run input through it, benchmark it against the known task, and probe it when adversarial prompt through red teaming. All of these are valuable, but they are sampling, not auditing. They can tell you how the model behaved on the input you tried. They cannot tell you what it will do on inputs you haven't through or you haven't thought of it. So sampling, it's basically it's not an auditing. So that's the limitation that every AppSec engineers uh, need to understand. So model card. So let's look into the model card as a solution of the industry came up with. So the documentation artifact designed to address this is the model craft, a structured document that accompanies a model and describe what it is, how it is built, and where it falls short. The concept was introduced by Google researchers in 2019 and has since become the closest things in the industry to standard transparency format. So here it is going to explain as a table what well formed the model card should cover. So you can go through the table. Just let me go through in a very fast section. What should be it tell to you? Training data. What sources were used? How they were filtered? Non-gap spaces. So intended use. What the model was designed for. Evaluation result. performance metrics across different conditions, and the demographic non limitation tells you conditions under which model is known to underperform or behave unexpectedly. Bias assessment, where training data or evolution may have introduced skew. License, what you are legally permitted to do with the model. So the room was great analogy. Think of it like a uh, nutritional label for a AI model. You can't see inside the product, but the label is supposed to tell you what went into it and what to watch out for it. So next one is the gap. So let's check the reality. So in practice, the model cards can also be frequently incomplete, vague, or in some cases absent entirely. And unlike food labels, there is no regulatory requirements to produce as of now. It remains voluntary for most use cases. The incentive to be true is a weak when disclosing limitations might reduce adaptation. So let's check the security takeaway. From a security standpoint, the spares or missing model card is in an inconvenience. It's a warning sign. So it means the organization distributing the model either didn't elevate it thoroughly enough to document findings or choose not to share what they found. Either the downstream user is flying blind. So here the room closes with this line. And yeah, and I love this line. In security, hope is not a control. Perfect. So let's look into the questions of task number 5. What documentation artifact accompanies a model to describe what is it, how it was built, and where it falls short? So that is basically the one which we describe is model card, MODELCARD. Correct. So what are the billions of floating point numbers that make up a trained model? So collectively referred to as that billions of floating means that weights, WEIGHTS. Yes, correct. Section number 6 or the task number 6, which is the practical exercise. uh, it's a hands-on part. Click the green view side view button above the open simulated model repository to build a resemble Hugging Face. One of the most widely used platforms sharing open source AI models, because anyone can upload a model. It's a powerful resource and real supply. Your job is to perform the model audit. Think of its scavenger hunt for red flags, the warning signs that security conscious engineer should never ignore. They could be looking in the model card and the metadata and the file listing or the training details. So I go through this simulated repo and flag everything seems suspicious. Here, here the thing what I found, and the room confirm it's these are the severity of each one as well. So you just open the uh, side view button, so you can view all the details. You just need to audit that one. So this particular question I will hand over to you. You can answer it, and you will get a complete flag. Like once you complete all the uh, six flag, or once you capture all the six flags, you will get the final flag. You can submit here. So that one I am going to skip because it will take too much time to review, or else I will do it later in another session or another video. So task number 7 is the conclusion. So that's a full walkthrough. So let's wrap up with this task number 7. So you have explored how the security risk of AI systems are shaped long before a model ever reaches the production, from the unaudited data pipelines that feed pre-training to the inherited vulnerabilities carried out through fine-tuning, to the simplest fact that no one can look inside the trained model and see what actually it's doing. The risks stack up at every stage of the build process, long before it anyone thinks to it ask a security question. So that's the whole point of this room. So AI security doesn't start at the deployment, it start at the data pipeline only. So if this video help you, drop a like, do subscribe. I will post some walkthrough. I will drop some security videos, application security videos, bug bounty breakdowns, and some AI assisted some pen testing content. So see you in the next one or next video. So peace. Thank you so much.